So today we're going to be analyzing some data of Disney movies. This presentation was created by Ashley Curry, Carter Duncan, Hazel Schaus, Hope Seiler, and Nina Parker. So to start off, on the right of the PowerPoint, you could see that this is kind of a snippet of the original data set that we use. And that data set was actually updated January of this year, which is honestly pretty up to date. And then the data that we use was scraped from Wikipedia and cleaned. And it consists of 432 observations and 32 variables. And it was all compiled together by a person named Samir Patel. And so you're probably wondering, like, why Disney movies? We didn't really know any of each other in our group. And when we first kind of started to talk, we all kind of figured out that we are interested in different majors and we're also different years here at UVA. And so we couldn't really find any academic topic that piqued all of our interests. So we decided to look outside of the academic realm to try to find a topic that could yield some possibly high observations. And I'm not really sure who, but someone threw out Disney as a whole broad idea. And we all loved it. And then we went on Kaggle, and then we found this extensive Disney movies data set. So from the original data set, we aren't going to be using all of the 32 variables because that's a lot. So we're going to be pulling the title variable, the release date variable, the runtime variable, the country variable, the budget variable, the box office variable, the IMDb score variable, the directed by variable, and also I'm blocking it slightly, but the cinematography variable. And so from actually the release date variable, we're going to be splitting that into a month variable and a year variable. We don't really need the date. It's not as relevant to what we're going to be observing. And we're also going to be adding two other variables that are kind of like create a range of the runtime and the IMDb. And so the range for the runtime variable is going to be called length, and the IMDb is going to be ratings. And on this slide, we really wanted to kind of show a clear distinction of what's going to be numerical and what's going to be categorical. And so, as you can see with the numerical variables, there's the runtime, the budget, the box office, and the IMDb. And then the other 8 are going to be in the categorical variables section. And now I'm going to be passing it off to Hazel, who's going to go more in depth into how we prepared our data.
Hi, I'm Ashley, and I'm going to be talking about the data preparation step of our project. So in general, we did some general cleaning, such as removing the word minutes from the runtime variable and converting the IMDb number to numeric. But we also noticed that there were 3 films with no listed runtime budget, box office revenue, and IMDb score, and another movie with no listed runtime budget and box office revenue. So we decided to remove these observations from our data set as they did not provide us with useful data. Further, we noticed that under the country, director, and cinematography vectors, there were sometimes multiple countries or people named. So in order to simplify the data for the data visualization piece, we decided to clean the data to only list the first country or person mentioned for that particular movie. So as you can see here, there's only one country listed now under the country vector and only one person listed for director and cinematography. We also made 2 new vectors from the original release date for movie release month and movie release year. And we also used the mutate function to create 2 new character vectors for movie length range and ratings range. So movies fell into the range of 40 to 60 minutes, 60 to 80 minutes, 80 to 100, 100 to 120, 120 to 140, or 140 minutes plus. Similarly, movies in the ratings vector fell into the ranges of 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, or 8 to 9. The next step we did was summarizing our key numerical variables of runtime, IMDb rating, budget, and box office profit using the summarize function. So the output of the summarize function includes the minimum value, maximum value, median, mean, and the number of non-applicable observations in the data set. Additionally, it included the first and third interquartile range, but I'm not going to present them for simplicity's sake of our presentation. But one interesting observation was that for the summary presents is the mean IMDb rating was 6.545. And this is interesting in context because IMDb rating scores are compiled by IMDb by gathering a mean for submitted individual ratings from viewers. So the average IMDb rating, according to imdb.com, of all movies is a 7, meaning the mean Disney movie score is slightly lower than the general population of movies. Another interesting point is that the mean budget is about 68 million and the mean box office profit is roughly 168 million. So these numbers indicate that in general, most movies are generating a larger profit than they are spending to produce the films. The next step we did was making frequency tables of 3 categorical variables. So the first frequency table we made was of country the film was made in and the number of movies made there. So as the data shows, the United States has overwhelmingly produced the most Disney movies. The second table shows movie length range and frequency, and it demonstrates that movies between 80 to 100 minutes are the most common. Finally, the third table of rating range shows the most Disney films earn an IMDb score between 6 and 7, which makes sense considering the mean score is around 6.5, as I just discussed. But there is also a large frequency of movies that fall within the 5 to 6 rating range and the 7 to 8 rating range. Finally, we made a two-way table of release month and rating range. So keep in mind when looking at this data that, as seen in the last slide, most Disney films had an IMDb rating of 5 to 6, 6 to 7, or 7 to 8. So that's why there is a high number in those categories. And nevertheless, we do see interesting trends in these 3 ranges. Notably, not many movies are released in January or September. Another observation is that high-scoring movies seem to be released in May, June, and July. And if we look on a more individual level, we see that most movies scoring 5 to 6 are released in March, July, and December. And most movies scoring 6 to 7 are released in June and July. And most movies scoring 7 to 8 were released in June, October, and November.
Hi, my name is Hope, and I will be presenting on the data visualization aspect of our project. So first, we will be looking at a bar graph, which shows 2 categorical variables. In this case, it is the country, which is on the x-axis, and the number of movies that each country has produced on the y-axis. And as you can see on this slide, we have removed the US simply because the US has produced the highest number of movies by far, so it's easier to visually compare the countries if we just remove it. So with that, we can note that the United Kingdom has produced the highest number of Disney movies, with Canada, Norway, Russia, and Spain producing the least. Next, we have a word cloud, which shows the directors of Disney movies in our data set. And there are a ton of different names, but the 3 that really stick out are Robert Stevenson, Norman Tokar, and Vincent McEvedy, which shows that they have produced the highest number of Disney movies in our data set. There are obviously some names that are just slightly smaller that have produced a high number as well, but these 3 really stick out. Next, we have 2 box plots. On the left, we have the movie budget, and then on the right, we have the IMDb ratings. So I will first start with the left graph, which is the movie budgets. And we can see as the median here is around 30 million, which is shown by the black line on the left side of the blue rectangle. And the tail is skewed to the right, but the majority of the data goes more towards the left at around 100 million. So while there are many budgets around 50 million, there are definitely outliers that with movies that are produced with much higher budgets, shown by the little dots, which Chicken Little is conveniently pointing to. And then these dots are also very evident in our second box plot, which is the IMDb ratings. And so the median here is around a 6.3, which is actually pretty high because this is on a scale of 0 to 10, and a 6.3 rating on IMDb is generally pretty high. And with that, there are definitely some outliers, as we can see by the green dots, showing that some Disney movies have lower IMDb ratings, but generally in our data set, they were higher. Here we have a side-by-side box plot, which is kind of the most dense of our graphs. So I'm going to try and take it country by country based on the data that we found. And so this is a graph showing the country based off of their budgets. So first off, we can see that India, Norway, and Russia spend the least amount of money for their Disney movie budget, all of them with a median of around 5 million with very little range. France has a much larger budget with a median of around 60 million and with a range of around 150 million. And then if we move to the other side of the graph, we can see that the UK's median is lower than France's median at around 25 million. And the box plot is skewed to the right with lots of movie budgets higher than the median. And then finally, if we look at the US, the median budget is slightly higher than that of the UK and France's, but it is extremely skewed to the right with lots of very high outliers. So just overall, we can see that the UK, France, and the US have the highest budget, but the United States has the highest outliers, which makes sense if we try and think about it in context, especially just thinking about the movies that the US has produced. If we think about like Frozen, which had a really high budget in comparison to some of the other countries. Lastly, we have a scatter plot based on budget and the box office profit, which is on the top of the slide. And so quickly, we can just see that Disney movies tend to have budgets on the lower side of the graph, but in reality, this isn't actually that low because this graph is shown in hundreds of millions of dollars. So they are more towards the lower side of the graph. But we can see that if a movie has a higher budget, it typically will have a higher box office profit. It's not that strong of a correlation, but we can imagine if we drew a line from one of the points that it would probably be a strong positive correlation, which isn't super evident in this graph, but actually once we turn over to the bubble plot on the bottom of the slide, we'll see that it's actually a little bit more evident. So with that, this bubble plot is showing the year of release in the budget in different countries. And the size of the bubble is based off of the box office profit. And so just generally, we can see an increase in spending in these different countries over the years. With that being said, if we look at the little key on the right side of this graph, we can see that the countries are based off of different colors. And so you will notice that this graph is mainly pink, which is the United States. And then also with that, and more generally speaking, the higher the budget, the higher the box office profit, which wasn't that evident in the last graph. But we can see here that there actually is a pretty strong correlation with that based on the size of the bubbles. And yes, that is our data visualization aspect of our project. And so now I will be handing it over to Hazel, who will talk about 1 and 2 sample imprints.
Hi, I'm Hazel, and I will be discussing the inference portion of our project. And before I get into the conclusions that we made, I just want to go over a few terms that will help us understand these conclusions. So first of all, we are looking at a sample of the population. And so here our population is all Disney movies, but because we can't collect data from an entire population, that wouldn't be practical. We look instead at a sample or a subset of that population, which here is the Disney movie data collected in our data set. And so we're interested in estimating a parameter or numerical attribute of the population, all Disney movies, by looking at a statistic, which is that same numerical attribute in our sample. And so the statistic that we're looking at to make a conclusion about the parameter is the percentage of Disney movies made within the United States. So that's what we'll be estimating based on the percentage of Disney movies made within the United States within our data set. And so what our outputs is the 95% confidence interval. And what that tells us is that with 95% confidence, we can say that the true parameter falls within this range of values. And so it gave us 0.894 and 0.947, which we can see on the left. And we can conclude from that interval that we are 95% confident the true percentage of Disney movies made within the United States is between 89.4 and 94.7%. And this makes sense because in our sample, our data set, we saw that a lot of movies were made in the US, and so it makes sense that the majority of movies generally within the larger population would be made in the United States. So the next inference that we made is based on two different samples. And so we subset our data to just have one with the US data on the Disney movies collected and one with the United Kingdom Disney movies collected from the data set. And our goal here is to find the difference in two means in the population. So what we want to figure out is if the average IMDb rating in the US is larger than the average IMDb rating in the United Kingdom. And so our 95% confidence interval gave us a negative value and a positive value. So that means that we cannot say with confidence that one is larger than the other because 0 is within the range that is predicted by R. And so we cannot say that one is larger than the other because if both were positive, then the US would be larger, would have a larger average IMDb rating. But because 0 is included, again, we cannot make a conclusion, and the results are inconclusive. So now I will be passing it off to Nina, who will talk a little bit about regression.
Hi, I'm Nina, and I'm going to be talking about regression using our Disney dataset. So the first thing that we did using regression was to create a simple linear regression model. And what this does is it basically uses one explanatory and one response variable. And the goal of this kind of regression is to understand the ways in which the explanatory variable can predict the response variable. So for our model, we decided to use IMDb rating as the explanatory variable and box office profit as the response variable. So the model is shown right here at the top of the slide in this equation, but before I get into anything else, I just want to explain what some of these numbers mean in context. So this right here is the y-intercept, which is about negative $400 million. And what this represents is the box office profit when the IMDb rating is 0. Now, this doesn't make practical sense really, just given that it's very unlikely that the IMDb rating would be 0. And it's also very unlikely for a movie to make a really large negative profit such as this. But nevertheless, that's what that means in context. Next, we have the slope, which is around $900 million, and this represents the change in box office profit when the IMDb rating increases by 1 point. This number is a little bit large for our liking, and it led us to be a little bit skeptical about the effectiveness of our model, but either way, we still continue to use it to make predictions about our data. So this is the output that we received when we set the IMDb rating equal to 9. Showing that our model predicts that a movie with that rating will earn $382,801,063 in box office profit when the rating is 9. While this prediction does make practical sense, we're still a little bit skeptical about the accuracy of the model. And one reason for this is because the output shows a very low R-squared value, which is shown here in red, and it's about 0.07. So what this means in context is that only about 7% of the variability in box office profit is explained by our model. And this number is fine, but ideally we'd like it to be a lot higher because we want more of the variability to be explained and accounted for within our model. But that being said, the model still worked in predicting box office profit based on IMDb rating, which was what our goal was with this simple linear regression. So next we looked at logistic regression, which is basically a kind of model that helps predict a binary outcome. And binary outcome basically means that you can either get one of two outcomes, a success, a failure, heads or tails, etc. So for us, this means that we're attempting to predict whether a movie will get an IMDb rating above or below a 5 out of 10 based on the explanatory variables of box office profit, runtime, and budget. So using this model, we set box office profit to $500 million, budget to $5.5 million, and runtime to 100 minutes. And all of these values were just picked randomly, but they seemed very reasonable values for those variables. That being said, they are a little bit high, so just keep that in mind with the output. So our model gave us an output of 0.995. And so what this means is that given the values we set for each of those explanatory variables, there's about a 99.5% chance that the movie will get an IMDb rating above 5. So from this, we can see that with the values that we chose, there's a very good chance that the movie will score a high IMDb rating. But once again, keep in mind that these values were a little bit high. So if you have a high budget, a high profit, and possibly a high runtime, there's a higher likelihood that you will get a good rating. So that concludes our project on the Disney dataset. Overall, we're very happy with all of our data visualization and our analysis, and we really appreciate you watching. So thank you.